3.10 trigonometric equations and inequalities, day 2. So let's go ahead and just recap yesterday, what we did yesterday, to remind ourselves kind of this process of solving that we saw. So looking at our different steps there, step 1 was to isolate the trig function on one side of the equation. And so if we look at problem 4b there with that tangent, that's what we did. Moved the 4 rad 3 over, then divided by 4, we got tangent by itself. Once the trig function was by itself, then we found the corresponding angle measures on our unit circle that satisfied the given equation. And then we were able to consider domain restrictions and then write the solutions and or general solutions for the problem. Noting in problem B that we had that equidistance apart, so we're able to just write one answer instead of two. So today we're going to expand on what we learned yesterday, and we are going to look really at two different things. One, as we see in this first problem, what if we have something other than just x or theta inside of the trig function? In this case, we have 5x, sine of 5x. So how's that going to affect the problem? And then later, we will look at what if we are squaring our trig function like we see in problem 2 here. What would we need to do with that? And then to continue with the squaring, we're going to look at some problems that might require, like problem number 3 here. This one is actually going to require us to factor. So we're going to have to brush off our factoring skills a little bit. Okay, but we'll get to that a little bit later on in the period. So let's go ahead and start with this problem 1a here. We want to solve this equation and find all solutions. So we're going to find our general solutions. Now the first thing I was reminded ourselves was that we want the trig portion isolated on one side. So how can I get those two sine functions on the same side? What would I need to do? Any thoughts? I would do the adding. Yeah, you could subtract. And that'd be fine, but I'm going to go ahead and add. So we're going to add the sine 5x that's over here. I'm going to go ahead and add it to the other side. Add sine 5x. And if I add sine 5x plus sine 5x, what is that going to give me? Any thoughts? How many sine 5x's am I going to have then? 2, right? It's just as if I had x plus x would be 2x. Sine plus sine, as long as the insides are the same, would be 2 sine. So I have 2 sine 5x plus square root of 2, and that all canceled out down to 0. Okay, I still want to get, now I only have one trig function, that's good, but I want to go ahead and still isolate it. So what would I need to do next to isolate that? Orlando, what would we need to do to isolate my trig? And how would I do that? Subtract it. I want to get it over on the other side, right? So that's 2 sine 5x equals negative rad 2. Again, we're still isolating our trig. So what would I do next, Gabriel?
Divide by 2.
Divide by 2, yep. All right, and I have sine of 5x is equal to negative rad 2 over 2. Now, what I've seen happen in the past, and I'm telling you right now this is wrong, so please don't do it, is I've seen so many people say, oh, 5x, that means I need to divide by 5. Divide by 5, yay! Cancel out sine of x. And that is wrong. Please don't do it. I cannot touch that 5 yet. We will. Just have patience. We'll get to it. We're not there yet. First off, we need to kind of undo the sign. And to do so, we look at our unit circle. So if you haven't gotten your unit circle out, please get it out. We will be using it quite heavily today. Okay. So looking at your unit circle, when is sine equal to negative rad 2 over 2? Let's look that over. When does that happen? All right, Mandy, where does sine equal negative rad 2 over 2? Okay, that's one of them. There's another place. Where is it? What was that? 7 pi over 4. So 5 pi over 4 and 7 pi over 4. So down in quadrants 3 and 4 because that's where sine is negative. All right. Now, at that point, to write all our solutions, yesterday we would say, all right, from there, x equals 5 pi over 4, but what would we need to add to get all our solutions? Plus that 2 pi n, right? Plus 2 pi n. And then we also said x equaled 7 pi over 4 plus 2 pi n. However, do I just have x here? What is inside my sine? So I wouldn't just have x. Instead, I would say 5x equals this. And that is the difference from yesterday to today, is that we have a little bit more work that we need to do. And we are going to divide, because we still want to get x by itself, so we have to solve. And how do I solve and get rid of the 5? What do we do, guys? We divide it. So I'm going to divide 5 into all of this on each one. Divide 5. Now here, that will finally give me my x. Now, we've done this quite a number of times. What is the same as dividing by 5? Multiplying by what? So I have 5 pi over 4 times 1 over 5. And this one I can just write as 2 pi n over 5. This one, 5's cancel, leaving me with x equals 7 pi over 4 times 1/5 plus 2 pi n over 5. All right, and then let's get our fully simplified answers. 5 pi over 4 times 1/5. What would that reduce to? Or what happens to those 5's there? Cancel out, leaving me with what? Pi over 4. And again, I could write this as 2 pi n over 5. I've seen that written as we see it already. I've seen it written as 2 pi over 5 and then n. I've also seen it written as 2/5 pi n. It doesn't really matter. They're all equivalent. So 2 pi n over 5 is what I'm going to leave it as. And then don't forget, in our final answer, we need to add in n as an integer. And then our last answer here, x equals, what would be our final result there with the 7 pi over 4 n times 1/5? 7 pi over 20, nothing cancels. I just multiply straight across. 7 pi over 20 plus 2 pi n over 5. N is an integer. And that would be our answer for problem A. So let's just go ahead and recap what we did. So most of the problem was pretty much identical to what we did yesterday. We did have two signs to begin with, but we just combined them up. Then we isolated by subtracting and dividing, got our trig function by itself. Then we looked at where does that happen on the unit circle. And then the only thing really added in today is that we had not just x, but 5x that we had to set equal to our answers. And I just had to divide by that 5 all the way through to be able to get to our final answer with x isolated by itself. So again, we will divide the 5, but we have to do it here at the end instead of over here with the sign. I have to get rid of the sign before I can touch the 5. All right. We're going to skip over B for right now. I want you to drop down to C at the bottom of the page, and I want you to try that out. Take the next couple minutes. Try out problem C, please. All right. Let's go ahead and do this problem. We need to isolate our tangent. Aaron, what would I need to do to isolate my tangent? Eventually, but not yet. There we go. Subtract the 3 first. 3 tangent. And then after that, Aaron, what are we going to do? And then we can go ahead and do that dividing. Okay. Divide by 3, tangent of this is equal to -1. Okay. All right, now we can go ahead and look at our unit circle, tangent values, and where does that happen? Sophia V, where is tangent -1? 3 pi over 4 and 7 pi over 4. All right, so let's go ahead and set up our stuff. And we're going to be having x over 2 for each of them. So x over 2, Jet, what would be x over 2 equal to?
3 pi over 4.
Plus?
2 pi n.
I could do plus the 2 pi n. If I do the plus 2 pi n, then I have to do the other one. And that would be?
7 pi over 4 plus 2 pi n as well.
Yep. And you could do that. Anybody want to give us the other way? What could I do with just one equation? How would I set that up? X over 2 equals what? Plus pi n. And remember, we can do that because they are directly across from each other and have that equidistance. So again, one or the other, it doesn't matter. How are we going to solve these equations? Sophia S., how would I solve these equations? Multiply by 2. I'm going to do it on all of these, so whichever way you decide to do it, you need to multiply everything by 2. Multiply everything by 2, and also on this version down there. So that would be x equals, let's see, when I multiply 6 pi over 4 would be 3 pi over 2. Plus that would be end up being 4 pi n, n is an integer. And then x equals 7 pi over 2 plus 4 pi n, n is an integer. Or in a single equation, 3 pi over 2 plus 2 pi n, n is an integer. And one or the other, I like doing a single equation, so that's the one I'm going to box. So I like that one, but both are correct and will give you the right answer. All right, any questions on this process and how it is different from yesterday? All right, let's go ahead and turn the page then. And we're going to look at what happens when sine or cosine or tangent are squared. So when squaring a trig function, we have to be very, very careful because sine of x squared, as we see in the parentheses here, is not the same as what we have here. Instead, if I'm going to be squaring sine, this is the way that we want to write it. I want to just talk about this a little bit up here. I'd recommend writing this. So if I write sine of x squared, and I put the square after my x, this is actually equal to sine of x times x. The x is what's being squared, not the sine. And this is not equal to having the squared after the sine. So remember, what the square comes right after is what is being squared. Now, I would not write that as sine times sine of x. That would be an incorrect way of writing that. Instead, we can say, hey, that would be sine of x squared. That's what that means, which actually means I am doing sine of x times sine of x. And this is more of what we'll be dealing with. When we square a trig function, that square, and it could be square, it could be cubed, it could be any power, that power has to come right after the trig part, not after the variable or the angle. Because if I put it after the angle, that means I'm squaring the angle, or the x, not the actual trig function. So, where we put the square is important. Don't misplace it. Because if you do, it would be incorrect. So let's go ahead and try solving an equation that involves a squared trig function. So let's go ahead and look at problem A. So again, process will be very similar. I want to get my trig function by itself. So Daniela, how would I get that trig function that I highlighted by itself? I wouldn't want to add the 4. The 4 is multiplying to the sine, so it's kind of attached to it. I will divide by the 4, but I want to take care of this 3. There we go. I want to get rid of that 3 first. So it's minus the 3 over. That'd be negative 4 times sine squared of x. And then after that, Daniela, what would I do? By the negative 4. So I get sine squared of x is equal to 3/4. All right, usually at this point we then looked at our unit circle. Is there a 3/4 anywhere on our unit circle? Yes or no? Okay. But that's also because my sine is still squared. And in the end, to be able to look at my unit circle, remember, all those values on the unit circle are sine values or cosine values or tangent values. They're not sine squared values or cosine squared values. So I need to get this so it is just sine. So how do I get rid of the square? I square root it. So same exact solving processes that we've done before. So this will get me my sine by itself. One thing we have to remember, what goes in front of the square root when we do this? Plus or minus. Often so many people forget the plus or minus. So please, I'm telling you right now, don't forget it. When we square root a fraction, we square root the numerator and the denominator. Now I can't do the square root of 3, so that's still square root of 3, but what is the square root of 4? Does that look like something from our unit circle? Yes, it is. Now, when you go to look from your unit circle, you now have to look for not only when is sine equal to positive rad 3/2, but also when is sine equal to negative rad 3/2. So there are actually 4 different positions. So look at your unit circle. When does that happen? All right. Let's see. Tyler, when is sine equal to plus and or minus rad 3 over 2? Okay, pi over 3. Where else? Uh-huh. Yep. So all are pi over 3s. 4 pi over 3 and 5 pi over 3. Okay. So let's go ahead and list out our answers then. Now this is just sine of x, so I just have x equaled. I'll start with pi over 3. What am I going to add to pi over 3? Nathan, if I state all my solutions, what do I need to add? Okay. What have we been adding each time? We want to state all our solutions. 2 pi n, because when we find all our solutions, we're talking about this point. Then I go a full circle to get another one, and then another full circle, another full circle. So we're adding 2 pi to get to these same places. Okay. Oops, too much. There we go. So we're going to go ahead and add 2 pi n. N is an element of the integer set, and I could go x equals the next one, 2 pi over 3, plus 2 pi n. N is an integer. And then I have 2 more, 4 pi over 3, plus 2 pi n. N is an integer. And x equals finally 5 pi over 3, plus 2 pi n. N is an integer. All right, so there's our answers. However, is there a simplified version of our answers? Can we write this with just 2 equations? Do we see any that are directly across from each other? Which ones are directly across? Let's see. Dean, give me 2 of those angles that are directly across from each other. All right, so we can condense those down, right? That can be condensed down. And what would be that single equation, Dean, that would work for those 2? It's pi n. N is an integer. And then what other 2? So the other 2 would be also directly across from each other. So we can condense those down. And Ava, what would be the second equation here that I could write? It's pi n. N is an integer. And again, I like to not have to write as much. So I like that more condensed version. But if you want to write them all out, you're not wrong. I just like to have it condensed down. Yes? Not on this one. Sometimes it is. But on this one it's not. And that's because it's a little bit hard to see on my drawing. But let me pull up the unit circle. If we're to look at the unit circle in those positions, so pi over 3, let me highlight. So I have pi over 3 to 4 pi over 3 directly across, 2 pi over 3 to 5 pi over 3 directly across. Now to be able to condense this down into a single equation, I would have to be equidistant in between every single one. And we're not, right? The distance between pi over 3 and 2 pi over 3 is 60 degrees. Whereas between 2 pi over 3 and 4 pi over 3, that's 120 degrees. So not equidistance, but if you do see that it's equidistant between all four, then yes, you can condense down to 1. Okay? Does that make sense? All right, let's go ahead and go back to here. So with that all in mind, I want you to again skip B, go down to C, please. Go down to C. All right, just looking at the time, I want to go ahead and look at problem 4. All right, so let's go ahead and solve. Zach, what would I do to solve here? Definitely, so 4 cosine square root of x equals 2, and then?
Divide by 4 on both sides.
So cosine square root of x is equal to 2 over 4. Now, some of you, and I totally understand this, will want to reduce this and get 1/2. How many of us reduce down to 1/2? Totally okay, okay? It does work, it's just actually harder if you reduce, okay? So, I'm actually going to keep it as 2 over 4 for right now. What do we do next, ladies and gentlemen, to solve? Square root it. I want to show you why this one is a little bit easier if we don't reduce here. So cosine of x, what is the, okay, plus or minus, square root of 2, so that would be square root of 2 over the square root of 4. Well, that's just square root of 2, but what is the square root of 4? Is that something from our unit circle? Yes. If you reduced, and this is I want to show you now, if you reduced and you did 1/2 and you took the square root, you would have noticed that that'd be 1 over the square root of 2. And that is not wrong, but it doesn't look like what's on the unit circle. To be able to get it to look like what's on the unit circle, you have to then rationalize the numerator, rationalize the denominator. So that would become square root of 2 over the square root of 4, and guess what? That is exactly what we have right here without the reducing. So, but regardless, one way or the other, we get to here. All right, on the unit circle, where does that happen? Here. Jathan, when is cosine positive and negative? Add 2 over 2. Pi over 4. What was the next one you said? Okay, 7. Where else? And? So all our pi over 4s. All right. So again, we could list all 4 out. Seems like a lot, but you could. Pi over 4 plus 2 pi n. Let's see, 3 pi over 4 plus 2 pi n. 5 pi over 4. Oh, I wrote that wrong. I put 5 pi over 3. That's 5 pi over 4 plus 2 pi n. And 7 pi over 4 plus 2 pi n. Now, and that would be correct. However, can we condense it? Can we condense it down to 2? Are there things that are directly across from each other? Okay, so then I could condense it down to pi over 4 plus just pi n, n is an integer. And then the other one I would want, so that would take care of pi over 4 and 5 pi over 4, because those are directly across from each other. And 3 pi over 4 plus pi n. All right, and that would be correct. However, that is not the most condensed that we can do. Ben, what answer did you give? I'm actually going to write this as pi over 2n. And I could just give this single equation as my answer, and I would be correct. So you could write 4 statements, 2 statements, or just 1 statement. And again, this is if you notice that we have that equidistance, which we do. If you look at the unit circle, these are the pi over 4s. They are all 45 degrees apart, or pi over 4 apart. Or no, not 45 degrees, 90 degrees apart, pi over 2. They're all pi over 2 apart, 90 degrees. They are 45. To get to the next one, you'd have to add 90. So if you notice that, you can condense it down to just a single one, which was the question Ben had earlier. And it can happen. And if you see that, take advantage of it. If you don't see it, it's fine. You can list them all out, or you can list just 2, or you can list 1. So if you give me one of these set of answers, I will take any of them. I'm not going to say one is better than the other. All right, let's go ahead and turn the page. And let's talk about instances where we might have to factor. So we're going to brush off our factoring skills. All right. So on this one, I see a cosine squared, but I also have just a plain cosine to the power of 1. I cannot combine those, but I want to think about it as if I had this problem. If that was my problem, I would want to add that to both sides. You don't need to write the x's. You can just look and set that equal to 0. How do we solve something like this? Well, we factor. In this case, what can we factor out? What's in common? X. And if I factor out an x, what do we have left? X plus 1. And now that I have 2 factors equal to 0, I just set both equal to 0. Do we remember doing this? It's been a couple months, but it is a skill that we can use here with trig. So that is a process that we're actually going to use on this trig function. So to start out, I'm going to add my cosine of theta to both sides. But just like those x's, I can't combine those. One has a power, one does not. So that is going to be cosine squared theta plus cosine of theta equal to 0. And just like the x's, what do they have in common that I could factor out? What's in common, guys? Say it again. Cosine. So factor out the cosine of theta. And what do we have left if we do that? A cosine of theta plus 1 equals 0. And it makes sense if we were to multiply this back in, we should get this up here. Hopefully we can see that. But this factoring instance is just the same as what we'd do if it was just x. So now that I have my 2 factors, I just set both equal to 0. Cosine of theta equals 0. And cosine of theta plus 1 equal to 0, which gives me cosine of theta equals to negative 1. And now we go to the unit circle and think, where on the unit circle is cosine not only 0, but also negative 1? When does that happen? Let's start with cosine equal to 0. When is cosine equal to 0? Or cosines are x value. When is x equal to 0 on the unit circle? Pi over 2, where else? 3 pi over 2. All right, so that's at pi over 2 and 3 pi over 2. All right, next is when is cosine equal to negative 1? At just pi. That's the only place. Theta equals pi. Now, let's look back up the instructions. Did they ask for all solutions? What did they ask? Solve on the... So that means I just look at one unit circle. I don't have to look at multiple. So those 3 angles are my answers. It's really right here. That is my answer. If it was find all solutions, I would then want to do the plus 2 pi n and yada yada. All right. So sometimes we are going to need to factor. And in this case, we are factoring out a GCF. But is that the only way that we have learned to factor? No. Let's look at problem C. Does everybody have, or problem 5, I guess it would be. Does everybody have problem 3? Okay, let's look at problem 5. Now, on this one, we have a sine squared. We have a sine, but we also have a negative 1. And that's different than like problem 4, where it's just sine squared and sine, and I could factor out a sine. Here, instead, it has all of them. So this is actually in what we call our quadratic form, where we have ax squared plus bx plus c. And we have to factor it accordingly. Now, at the beginning of the year, we saw that there are multiple ways that we have of factoring this in here, depending on who you had last year as a teacher. I'm going to go ahead and just show the box factoring way. Now, in our box factoring way, we always put the ax squared term up here. So I'm going to have my 2 sine squared of x. And then we put our c down here. And then we have to figure out what goes in the other ones. And we do that by taking our a multiplied by c. 2 times negative 1 would be negative 2. And we have to think what 2 numbers multiply to negative 2 but add up to negative 1, our b value. What 2 numbers do that? Multiply to negative 2. Sometimes you guys did it on the x. A times c and b, negative 2, negative 1. What 2 numbers multiply to negative 2 but add to negative 1? Negative 2 and 1. However you want to do it with the table or with the x, doesn't matter. All right, then that means I have negative 2 sine of x, positive 1 sine of x, and let's go ahead and factor. So what is my GCF for the first row? What can I pull out? A 2, and what else? Sine of x. What can I pull out of the second row? A 1. What can I pull out of my first column? Sine of x. What can I pull out of my second column? A negative 1. So my factors then end up being 2 sine of x plus 1 times sine of x minus 1 equals 0. And just like the last problem, guess what? We set each equal to 0. So 2 sine of x plus 1 equals 0. Sine of x minus 1 equals 0. And that will give us sine of x equal to negative 1/2 and sine of x equal to positive 1. And so then on the unit circle, you have to figure out where is sine equal to negative 1/2 and positive 1. And that happens up at pi over 2 and over at 7 pi over 6 and 11 pi over 6. Now this is solve. It just says solve. It doesn't give us an interval. So you would have to list out all possible solutions. One way of which of doing that is saying, okay, we have pi over 2 plus 2 pi n. N is an element of this set of integers. 7 pi over 6 plus 2 pi n. N is an element of integers. And 11 pi over 6 plus 2 pi n. N is an element of integers. And that would be the correct answer. This one can be written as just one solution. If you want to think about what that would be, you can. But I'm going to go ahead and leave it there with those three statements as my answers. All right, everybody. Have a fantastic day. And we'll see each other tomorrow.